Okay, so let's have a look at this next question. We have monochromatic, coherent light that is incident on two narrow slits. The interference pattern is formed on a screen behind the slits. And for this question, we're ignoring any diffraction of light around the slits. Okay, and that's due to each individual slit. All right, so at a point P on the screen, the electric field components of the EM waves from each of the slits can be described by these functions. E1 equals E naught sine omega t, E2 equals E naught sine omega t plus 0.272. The first part, are the light waves still coherent even though there is a phase difference, why or why not? Well, what does coherent mean? Coherent means that they have a constant phase difference. The key word here being constant, and since the phase is not changing, that would mean that yes, they are still coherent. Okay, cool. Next part. When one of the slits is covered, the intensity of the light on the screen is 21.1 watts per square meter. Okay, so we know then that that must be I naught. Remember, I naught is the intensity on the screen, the max intensity on the screen when one of the slits is covered. So therefore, I naught is 21.1 watts per square meter. Okay, we want to know, well, what is the intensity at point P? Okay, so we have an equation for this. Our equation for this is I equals 4I naught cos squared half phi. So therefore we can just sub everything in. 4 by 21.1 times cos squared half phi. So our phi is 0.272. And then when we do that, we get something along the lines of 82.9, and that's the three significant figures, watts per square meter. So that's the answer to that part. The next part, what is the separation of the slits if point P is at an angle of 0.2 degrees from the central maximum? Okay, so I'll just draw what our sort of slit setup looks like. This is our central point. Here we have a maximum, and then this is sort of what it looks like. So we've got some sort of point here, and this angle here is our 0.2 degrees. Okay. And the wavelength of light is 627 nanometers. We want to know what is the separation of the slits. Okay, so we can work this out from, well, what we know. So we have our equation, and I'll write it here. This is what we just wrote before. Now, phi in this case is given to us by, remember, phi on 2 pi is equals our path length difference divided by our wavelength. So therefore, phi is given to us by 2 pi delta L divided by lambda. Now, assuming that this is a small angle, which it seems to be, we can say that delta L equals d sine theta. And that's how our theta comes into it. So we have 2 pi d sine theta divided by lambda. And then what we can do is just solve this function here for d. Okay, so we know what our phi is. So our phi is our 0.272, and this is if our phi is in radians, remember? And then we can divide by 2 pi. We can multiply all of this by our lambda, so our 627 by 10 to the minus 9, and divide that by our sine theta. And then when we do that, we get, and we have to put our answer into micrometers. And then so when we do that, we get something along the lines of 7.78 micrometers. So that's the answer to that part. The next part, what is the maximum intensity of the diffraction pattern? Okay, so I'll just do this here. So the maximum intensity, remember, is when this part here, the cos squared half phi, when that equals, the max is when that equals 1. So therefore I max is 4 I naught. So it's going to be 4 times our 21.1. So we're going to end up with 84.4 watts per square meter. So that's that part. And then finally, what is the path length difference between the two waves at point P? Okay, so our path length, remember, is d sine theta. Therefore, we can just sub everything in that we know. Or we can also work it out by using this. So our phi divided by 2 pi equals delta L divided by lambda. So there's quite a few ways that we can work it out. So delta L is also going to equal phi on 2 pi times our 627 nanometers. And then when we do that, we want to give it in units of number of wavelengths. So we don't even need to do that. We just need to equate this, the phi divided by 2 pi. And when we do that, we get 0.0433. And that's how you do this question.